Good afternoon from Brussels. It's me again, Jean-Louis Van Bella. I'm a bit on a roll. I'm on a holiday, and so I thought I would continue to do what I've been doing the last week, is a bit promoting my papers and giving you some ideas to think about if you're into quantum physics. And I also going to talk a little bit about cosmogenesis and some recent discoveries that are quite startling and massive amounts of dark matter, dark energy in the universe, and how we could possibly explain them. So let me get going. I want to start with talking about uncertainty. That's been like a constant in my research, is to sort of deconstruct that notion a little bit. And when I mean deconstructing, I'll come back to this slide. I'm gonna first show you the yeah, it's a bit of a seminal paper, I guess. It's also the one that has the most reads on my recommendations on my ResearchGate site. Is the Bruys matter wave. I talked about this in previous videos. I said the Bruys hypothesis that matter particles should also have a frequency, just like light particles, like photons, is a great idea. But the confusion, and I think I refer to that as the original sin in quantum theory, is that people were still thinking in terms of linear frequencies, while if you think about orbital frequencies, things going around and around. I'll talk about that. You can look at an orbital frequency as two linear frequencies or two linear oscillations combined in one horizontal vertical one, going up and down and going sideways at the same time, will make something go round and round and round. And what is that something? It is a charge. However, the idea of a particle has permeated and subsisted in modern quantum theory. And so in that paper, I deconstruct that a little bit. While I don't actually, I do go back to the idea of a particle and ask this philosophical question, what does the idea of a particle, what is it? What do we think of when we think in physics in terms of particles rather than, in terms of charges and fields? Well, the first thing is that a particle would include the idea of a more or less well-known position, and that's where uncertainty comes in many variations. So the assumption is indeed that you think of a charge without any other properties, no rest mass, only a pure charge. Then I said that before, the Planck-Einstein relationship implies that that charge is not going to be sitting still. It incorporates energy, an electron, proton. I will give those models. And so we see when there's no rest mass, the slightest force on a charge will accelerate it infinitely, and so it will theoretically attain the speed of light. So when that charge goes around and around at speed of light, then we do not know its position exactly. Heisenberg made sort of a remarkable evolution. Schrödinger was originally with him, I think, but then sort of dissociated, together with Hendrik Antoon Lorentz and Einstein in the later Solvay conferences, from the philosophical position that Heisenberg took, together with Bohr. It is interesting because Heisenberg originally contributed a lot to the modern concepts. And he said, well, uncertainty, he first said, and that's correct, I think, the precision of our measurements may be limited. When you're measuring the size of a billiard ball with other billiard balls that you fire at it in the dark, then how do you know the size of the billiard balls? You need a measurement instrument that's more precise than the thing you want to measure. So Heisenberg referred to that as an Ungenauigkeit originally. The second thing he said is, measurements measurement may disturb because we're really talking about the micro scale, and when you measure something, you fire a billiard ball at a billiard ball, the other billiard ball, the original ball is going to move. So the information you measure gets lost. And so that then reduces, that introduces an uncertainty in our knowledge, not in reality, the other billiard ball goes where it goes, but our knowledge about where that billiard ball originally was gets lost. And so Heisenberg originally referred to that kind of uncertainty as an Unbestimmtheit. So then the third position, and that's the most problematic one, and the one that characterizes modern quantum theory, and I said for me it's more of a philosophical inconsistency than a methodological one. But it's this uncertainty is inherent to nature. It's just even in theory we cannot know what things are. There's no determinism anymore, and that's what Heisenberg referred to as Ungewissheit, and that was strangely enough, I think, elevated to some kind of dogma in modern physics. And I write it there. I think the third thing is an unproven hypothesis, and I think you can never prove it. It's indeed sort of a dogma, and that's what Lorentz, just before he died, actually, at the 1927 Solvay Conference said, why should we elevate, especially in science, indeterminism to philosophical principle? Science, if you want to move and advance and explain things, it's not a good idea to sort of say, some things you can't explain, because that sort of defeats the purpose of science. In any case, what I write here, we should not be too worried about the root cause of the real or the perceived uncertainty. The point I make in this paper is actually, so the Bruys hypothesis led to the modeling of a particle as a wave packet, with slightly different frequencies that make sure that the wave packet would stay together, except that it doesn't. And the Dirac equations, when you work them out, you have you have the elementary elementary wave function as a stable solution, but everything that sort of involves wave packets, these wave packets disseminate. So I'm not gonna continue that. That's the paper here. I work it out to dissipation relation and etc. And so the idea of a composite wave, you must introduce it when you think about linear frequencies. But when you think about an orbital frequency, you don't really need that, and things come together kind of nicely. To go back to uncertainty, I said my position is quite clear. Physics as a science should not incorporate a principle, a godlike principle, where basically you say, we can't know it, and the only thing we can do is model the world in terms of probabilities. The question is, where do these probabilities come from? So that's the shift that took place, where they say, we don't worry anymore about where the probabilities come from. And I think probability should be rooted in something physical. Think about you see in television when you buy a lotto number, these balls that move in a machine, and at some point little hole opens and a ball comes out, and that has a certain number. We all know that, like also computers, random generated computer numbers, there is a physical mechanism behind. There's electric currents and very high frequency computer clocks, chip clocks that it's kind of annoying. Get a lot of emails here. Let me close that. Let me close these emails. Where was I? So random. The idea of randomness itself, as we see it, if we would know that there's like a godlike intervention, determining what kind of random generated number you get out of a computer, or what number corresponds to hopefully the number on your lotto ticket, then you would expect, there's bias, there's a hand, there's a physicist talked about Maxwell's demon. It doesn't exist. So that's a philosophical point. When you look at physics, just the idea that you're not interested anymore in where the probabilities come from. That's sort of a self-defeating philosophical principle, I think, in science, and it explains a lot why I think the public turned away a little bit from modern quantum theory, in the sense that they say, well, you calculate stuff, but calculating stuff is something different than explaining stuff. I did a paper on sort of the difference between a calculation, an explanation, and a theory. These are three different things, and I think we should still look for good explanations based on theories that make sense, not just calculations. The thing I want to talk about here, because this is all fairly obvious, is there's another thing about the notion of uncertainty that I think confuses a lot of people, and it's sort of rooted in, I think Feynman and other sort of third generation quantum physicists that sort of assume that small uncertainty in the beginning makes for a very large uncertainty in the end. And that's, funnily enough, something that is also not true. I'm gonna quote just as an example here. Suppose we have a finite accuracy, he calls it. And then you can look at these definitions of uncertainty that I gave you. Is it the fact that the measurement disturbs or whatever? No, but we have a finite accuracy, and we do not know exactly where, maybe a very small uncertainty, just one atom is, say, to 1 part in a billion, something very small. And then as it goes along, it hits another atom, and because we did not know the position better than 1 part in a billion, we find an even larger error in the position after the collision. Yeah. And that is amplified, of course, in the next collision, so that if we start with only a tiny error, it rapidly magnifies to a very great uncertainty. Now, I found that it's actually in his volume 3, his volume on quantum mechanics, and it's sort of one of the introductory chapters. And so it's quite important because, I wonder, like, why would that be so? And I looked, is this some kind of mathematical model, a probabilistic model that, gives you that result? And I didn't find one. And Feynman himself, in the very first volume, gives a very good introduction on probability theory and statistical models. And here he introduces Einstein's random walk model. And, I will illustrate it because I had some difficulty. I don't want to pull up Feynman's lectures anymore because apparently MIT doesn't agree, or the guy who protects the copyrights on Feynman's lectures doesn't want me to quote from it anymore. But the formula you have there is basically that the distance, if we take successive steps, and at each step there's a random, it's random, it goes north, south, or west, east, or a number of other possible directions. And after n steps, you wonder what's the distance from where this particle started. You will find that it's the square root of the number of steps, so that diminishes, and it's quite important. Let me show you the Wikipedia. I hope I don't break any copyright there. Where is it here? Random walk. Yeah. This is Wikipedia, I think, on modern quantum theory. Presents some mainstream results which you can argue about, and I feel it doesn't give you much in terms of alternative theories, and doesn't. But on mathematical articles like this, the random walk. Here, let me give you that animated version. This is what is it? Millions of steps that are being taken in a random way, and you can see, and that's what Einstein modeled also. Einstein in 1905, his annus mirabilis, he did a nice work on the Brownian motion, modeling that. and that was sort of a bit of a gap in kinetic gas theory and emulsions. And he came to the same result that these particles in the Brownian movement in a glass of liquid dust particle, it's not going to walk away very far. And the more iterations you have, the smaller the radius of that random motion is going to become. So that's the thing that I wanted to highlight, is just don't take anything for granted. Said uncertainty itself as a philosophical principle, I think it's you may believe or not believe in God, that's your business, but in science it's a philosophical notion that you shouldn't entertain. And then the second thing is, if modern quantum theory is really about working with probabilities and stuff moving in random ways, then the hypothesis that this will lead to chaos is disproved by nature itself. I'm talking here as a human being. I'm a very complicated system, but I'm not a disorderly system. The interesting thing about and that's an intuitive thing I also wanna give. Gauge theories in quantum chromodynamics and other models, we know that electromagnetic theory does not depend on a gauge. A very intuitive way to explain what a gauge really is you'll see these models, the random walk, is well, it depends, what distance unit are you going to use. A particle moves from point A to point B. What is that fundamental distance unit that you are going to use? And that's sort of an intuitive approach, I think, to what a gauge would be. And it's also one of the issues I have. Of course, choosing another gauge, another distance unit in these probabilistic models is going to lead to entirely different results in terms of where a particle is after so many steps. And that's sort of the another kind of inconsistency, apart from dealing with infinities that come out of Dirac's equation and other things in renormalization. It's funny math. If your theory is really dependent on some fundamental distance unit or another, let's call it the gauge, then you don't have a fundamental theory. I want to make a note here, because I also going to talk about you have them somewhere, the Solvay, the very first Solvay conference, and sort of how the that's going to be at the end of my lecture, how you sort of see, I like this very first Solvay conference because you see the birth, I would say the philosophical birth of the very fundamental principles that have led to my theory a little bit and my worldview. So in this very first Solvay conference, you can see that they discuss what they call then la théorie des quanta, quanta, quantums, and I'll talk about it. They immediately say it's not a quantum of energy, it's a quantum of physical action. So it's the product of a force times a distance unit and times a time interval. So, but entropy now, and this is something I think is very interesting, since 2019, they basically, that's an evolution that comes out, maybe not of fundamental physics, but out of physics, I would say. That is, they really define it as scientifically as a measure, indeed, of what you could vaguely call, disorder, randomness, or uncertainty. I take the definitions from Wikipedia here, and disorder, randomness, uncertainty. We have a scientific measure of that, but as said, I look at my papers sort of to define the concept of what is disorder, what is randomness, uncertainty. That should be defined much better. Are you talking? Do you have a deterministic model, a statistically deterministic model? That's I think what we have in physics. We have determinism, but it's statistically, because the velocities are so high, the frequencies are so high of the charges in particle models. But I want to highlight here is then, since the 2019 revision of the Système International of Physical Units, the magnitude of you see the unit in which you're going to measure entropy is joules, energy by degree Kelvin. All these notions, temperature shelf, and the formulas that appear in the measuring of entropy, Boltzmann's constant, Avogadro's number, etc. The definition, the uncertainty in their definition is zero. The magnitude of the Kelvin, Boltzmann's constant, Avogadro's number, they are all now codified in one system, and they're no longer based on what people call like a physical artifact. Like 1 kg is this block of I don't know what was it, silver and a few other metals placed under 3 glass bells, and that's the kilogram. No, it's all based on physical classical theory, incorporating the Planck-Einstein relationship, of course. And that's really it. Maxwell's equations, I said that a couple of times, combined with the Planck-Einstein relationship, give you everything. So I to illustrate that, I'm gonna walk over my worldview again. I said there's two things. A lot of interest went into analyzing what I call disequilibrium states. Unstable particles or intermediate products in a nuclear reaction or whatever particle reaction. So in a disequilibrium state, you cannot apply the Planck-Einstein relation. It's slightly off. And Planck-Einstein relation is that the energy will be quite precisely equal to a frequency of an oscillation of a field or of a charge times the reduced Planck constant when you're talking orbital frequencies, things that go around, or the non-reduced Planck constant when you're talking a linear frequency. So my electron model is about the two stable particles and their antimatter counterpart. I'm going to talk about a hypothesis for dark matter later, but that's what we know. We have electrons and protons, and their their mass this appears as or the energy, I would say, appears as two fundamental constants in nature. And these models are mass without mass models, or I wonder, where does the energy come from? What gives an electron its energy? And my theory is quite simple. There's a point-like charge inside. I talked about that. It's confirmed, I think, quite conclusively by the phenomenon of Compton scattering and also Hart scattering, Thomson scattering. So you have a charge, and that's what I show here, going around and round, because it's the orbital oscillation is the sum of a vertical oscillation and a horizontal one. Two perpendicular oscillations in 2 dimensions, in 2D space. It's a planar thing. The charge inside spins around at the speed of light, c. And so it's the product of the orbital frequency and the radius of the oscillation. So then you only need the mass-energy equivalence relationship, because I said mass is the inertia to a change in the state of motion of that electron. That's it. Mass itself is it's electromagnetic mass. We've got a charge spinning around and around. It's kept in place by an electromagnetic field, the same electromagnetic field that the spinning charge produces. And then we have the Planck-Einstein relationship. And then put it here a bit in a different form, is a m. If you replace c, you have a squared times the orbital frequency squared. We can take one of these frequencies and substitute it by the energy divided by the reduced Planck constant from this relationship and the Planck-Einstein relationship. And the other one, we just use the formula we used to go here. I'm quite explicit on this because I got the reproach, well, your model is a lot like numerology. It's not. It's two equations, two fundamental equations of physics. We've got the two unknowns, and out of that we get one unknown, the radius. This one is a constant as well, the electron mass. And if out of that you get the Compton relation, you get the size of an electron. And I found that a remarkable result, and it's consistent with the magnetic moment and other physical properties of an electron. So let me write it out. M times A, what I do have here, I made a mistake, A square. Yeah. no, the yeah, sorry, square is no longer there because we've got a, oops, let me do that, a, and so the square here goes away. So we got m times a, mc square h times c, and again, we substitute the energy by mc square, and we've get this. So for the proton model, it's a bit more, I wouldn't say more complicated, but well, yeah, more complicated, and also some. I have some more issues with that in the sense. I mean, it's my own model. Huh? The Planck-Einstein relationship, we know when we apply it to electrons in orbital motion in an atom or molecular orbitals, it will be the action that is packed into that motion will be a multiple of h bar times the frequency. So you can look at my papers. I worked that out for Schrödinger's model of a hydrogen atom. And so the thing is, recently they did measure the proton radius much more precisely. It's much smaller than an electron, much smaller, which suggests that the proton charge is not like the positron charge. It's a much smaller thing. You can't pack it into a proton. Proton is much smaller. But to make a formula like the one I wrote for the electron work, I noticed. Let me clean up my notebook. Yeah, that's it. Some more. Okay, there we are. I noticed you need to insert a factor 4, n is 4, and then it works out. A over c must be that frequency here, a Planck-Einstein relationship with a factor, and we arrived at the ratio of the radius of the oscillation times the velocity of light. It must be 4 times h bar divided by the energy, and there then you get nicely the radius of a proton. So it's like a 3D oscillation, and that's sort of, I explored that in papers. Where does this factor 4, I would call it a form factor, where does it come from? The easiest explanation is still that when you look at the formula for the surface area of a sphere, you will have 4 times pi r squared, and the surface area of a circle, a 2D thing as opposed to a 3D thing, is only pi r squared. So that's where the factor 4 comes from, I would say. And again, you can dismiss it as numerology. I'm quickly going to show that I'm going to talk about it later. Yeah, I have a paper here, the proton yarn ball puzzle, as I call it, where you do want to find the equations of motion of that point-like charge inside of a proton, and that's sort of a difficult thing because a number of authors, which I admire very much, come up with a sort of a toroidal model, but I don't like that because it introduces like 2 frequencies. Let me show that. Frequency, you see you have 2 frequencies. You have the motion going around, and then the motion around the axis of the the axis of the toroidal, and then the frequency around the circumference of that toroidal thing. So I think my model is simpler, but I did try to. I'm not very good at that, graphing things and seeing like, is it like an accordion going back and forth, or is it something else? I do not have the answer. I don't sort of see how we arrive at the final model for the equations of motion of the charge inside of a proton. I'm going to combine it, of course, because it needs to be consistent with with the magnetic moment of a proton. Now the problem is first the magnetic moment of a proton is not measured as precisely. I mean, it has a larger uncertainty on the measurement. So I have some rough calculations here in that paper, but I do invite you to look at it. But that's going to be ultimately the answer. If you're going to have a proton model, it needs to be consistent with the measured magnetic moment. And that's, as said, that's a measurement that is much less precise than the measurements we have for electrons. So I'm less confident about my proton model, but at the same time, it's what Dirac would say, it's so beautiful and so precise that this equation here and this derivation must make sense. So that's sort of the model. The thing I want to add is that in this model where we have a sort of a two new dichotomies between matter and light particles, and also between electron charge and a proton charge and their antimatter counterpart. But yeah, we have two new dichotomies, which I want to talk a bit about. In this philosophical concept of bosons and fermions. So we have indeed corresponding light particles, linear oscillations of a field. The field is, what is a field? It's a force without a charge to act upon. And that's it. And what charges do we have in nature? Well, electric charges. We don't have color charges, gluon charges, strange charges, whatever charges that you have all these non-conservative forces in modern quantum field theory, which said the idea of a non-conservative force does away with the combined with laws of conservation of charge, of linear angular momentum, of energy. And I think these must hold. And so the only way out there is to continue to assume that, conservation of charge must be there, conservation of energy must be there, linear angular momentum must be conserved, but we cannot use the Planck-Einstein relationship. These oscillations are slightly off, I would say, and so they, nature works such. The Planck-Einstein relations make sure that these intermediate particles indeed disintegrate. There's no need for a weak force or a weak interaction to be assumed. They disintegrate back into stable stuff. And then the Planck-Einstein relationship is conserved again. So that's my worldview. For those who are interested in boson Bose-Einstein relationship, I am my reading Feynman.org site. It got mutilated. Again, I said there's a guy who protects the copyrights of Feynman's lectures, and he went as far as erasing a lot of stuff on my blog, although I clearly mentioned the source. But in any case, this is Maxwell, Boltzmann, Bose-Einstein, and Fermi-Dirac statistics. One that explains, how these strange statistics for bosons versus fermions actually can be explained by just distinguishing between matter and light particles. Light particles, you can pile them one on top of each other. Photons, maybe they have a very, 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 very small scale. I'm not saying they are infinitesimally small. They could be. It's a philosophical question that is out there which will never be answered. But if you assume that photons can be piled one on top of each other, you arrive at a Bose-Einstein distribution function. And for fermions, not. For fermions, you will... where do I have that? Yeah, you will see we have electron pairs, and you cannot just pile them on top of each other. Here you see these energy states from 0 going to 9, and we can only have one pair of electrons in any one state. And of course, there can be gaps in the shells. Atoms can be in an excited state. So here in the first column, you see the third and fourth energy state or shell, subshell, is not being filled. The second one only has one electron. The fifth one also one. But you can explain these fermionic distributions clearly in terms of combinatorial logic or probability theory. So I'm not going to talk too much about that because I'm rambling already for half an hour now. Let me go back to what I wanted to do, I think, is to talk a little bit about the interesting thing, the first Solvay Conference. It's not going to take me very long. But I find it interesting because I hadn't actually looked very much at the first Solvay Conference. I did, and this is something also if you're interested in the history of thought. Let me see here. No, I haven't pulled it up. Ah, yeah, here. A brief history of quantum mechanical ideas. I talk about, the really interesting young researchers, Oliver Consa, who who looks at other conferences in modern physics after the Second World War, and who wonders a bit what happened there and what led to Bohr and his fans winning out against the more common sense ideas of Einstein. Talking about that, actually, Einstein and Bohr, the discussions between the two at the latter conferences, Solvay conferences before the Second World War, you don't see Einstein engaging in much and in constant to popularity, where Bohr and Einstein battled vigorously around the ideas of quantum states and all that. You don't see that in the actual papers. It seems that Einstein had an issue. The first Solvay conferences after the First World War. German physicists weren't invited, and despite the fact that Einstein was no longer a German, he was a Swiss citizen immigrated to the US. He was very much against that, so he didn't show up at the first Solvay conference after the First World War. And in the others, he did not participate a lot. But I find here in this paper, this is one for the historical interest also, the first Solvay conference after the Second World War, which sort of marked the decline, I think, of the I would say the preeminence of the Solvay conferences on physics as sort of the prime theater in which fundamental ideas were being discussed. But so that was a pretty bad. If you look at the papers and the discussions, it's dominated by Niels Bohr and Robert Oppenheimer on the one side, and then Bohr presents his stuff, and Paul Dirac gets pretty much upset. Probably just like, I don't know if Schrödinger participated in this one, but by the interpretation that Oppenheimer and Bohr give to his wave equation, and he admits there's something wrong with my wave equation. Only a small part of the wave function has a physical meaning. How can we pick out the part that has that meaning? And basically, he's no match for Oppenheimer. Oppenheimer destroys him and brings in new theories, which are purely based on probability, amplitude, and stuff. And so that's an interesting read, because the most interesting is is not the discussion between Oppenheimer and Dirac, I think, but Rutherford's idea in the 1921 Solvay paper, paper for the Solvay conference on. Because I'm going to talk about the ideas of an atom and a molecule actually they hadn't been confirmed that long that atoms and molecules actually exist. And so you see in the 1921 conference these ideas that were there in the 1911 conference taking a much firmer shape. What else do I have in terms of contributions? Joseph Larmor, of course, the Larmor precession. Very interesting to look at these original papers. And Lorentz, of course, I translate because that's funny. A lot of these Solvay conferences still haven't been translated fully into English. It's hundreds of pages, of course. And so I think here the general discussion on the new ideas on causality, determinism, and probability, or I would say the new ideas on causality not being there and everything being not deterministic and only expressible in terms of probabilities, because that's the idea. Lorentz makes a very violent intervention, well, not a very violent, but a very sensible intervention. And he says it here: I'm prepared to admit that the conditions of an experiment are such that from a practical point of view, indeed, the old notions of uncertainty as expressed by Heisenberg, not the metaphysical one. We would have indeterminism, but that would be statistical determinism, right? So I would still keep my deterministic belief in fundamental phenomena, of which we cannot talk, perhaps, but perhaps a deeper mind would know the movements of these electrons, charges. So he argues basically determinism must be kept as an object of faith, but then not faith in the classical sense, just as a principle of science. And we should not elevate indeterminism to a philosophical principle. And there's nothing wrong. I put the French translation there, so you can check these things out. And that's actually where I'm going to go to the first Solvay conference. I said it is interesting. It's 500 pages, and I quickly gonna go over the main table of constants. So it was held in 1911. It was actually, that's kind of funny. I'm intrigued by it. I'm a biker. I go to the Forêt de Soignes, and so all the proceedings were held on the property of Ernest Solvay, a chemist who made his fortune with a patent in chemistry, and in the Metropole Hotel, which is about 1 kilometer from my home. And it was about the theory of radiation and quanta. There's an interesting introduction by Ernest Solvay himself, and he mentions, actually, it's kind of funny. He distributes to these, I think there were more than a dozen Nobel Prize winners or future Nobel Prize winners in the conference, an étude gravito-matérialistique, in which he sort of combines gravity and the theory of matter and light, I would say. La constitution de la matière, de l'espace et de l'énergie. Now, I didn't find that study sur l'établissement des principes fondamentaux de la gravito-matérialité, but it's clear for the scientists they don't react much to it. Gravitation for me is a force outside of this great unification theory I sent here. There is only one force, the electromagnetic force, and what happens in the nucleus can be explained in terms of dipole moments and other stuff, but it's electromagnetic theory. That's the only theory. And gravitation is basically, for me, Einstein was right when he developed his general relativity theory, a property of space, of the universe, and I'm going to talk a little bit about that at the end. Hendrik Anton Lorentz, famous Dutch scientist, explains the goal of the conference. He said, we want to discuss the questions linked to la mécanique et les propriétés de la matière, so mechanics and the properties of matter, the fundamental equations of electrodynamics, and our ideas on the nature of the ether, if it's still permitted to use that word. And from the proceedings, it's clear, ether is an abundant superfluous idea. So he talks about this new mechanics, which later turn out to be quantum mechanics, which takes the place of the old one. I said it doesn't take the place of the old one. I think it complements Maxwell's equations. Maxwell's equations are written in terms of continuous charge densities, continuous currents, and the Planck-Einstein relationship quantizes these when you go at a very, 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 very small scale. Nernst, very famous Nobel Prize in 1920, heat theorem, third law of thermodynamics, just like Solvay. He was a very wealthy man because of great practical inventions and patents. I'm mentioning it because this is probably the difference between modern science and modern physics and these guys did experiments, and they also what I note, and that's why these lectures are interesting, these conferences, they really go through great pain to explain what they measured, how they measured it, how they purified. I'll talk about it in the case when they talk about superconductivity, how they purified the metals to get there, and what the difficulties were in the measurements. It's really all verifiable, I think, unlike modern day experiments where you have CERN and SLAC and only just now releasing in the last 2-3 years all of their data into the public domain. No, here at the Solvay Conference in 1911, all data is public. There's a very friendly atmosphere, and people criticize each other freely. So his discourse is interesting. He mentions the link, and it's what characterizes this very first Solvay conference, the link between chemistry and atomic theory. So a lot about the black body radiation problem, specific heat of gases, but very interesting because the black box radiation problem got in the end solved by a variety of authors, not only Einstein, by the Planck-Einstein relationship. So, not going to be too long, go over it. Lorentz starts sur l'application au rayonnement du théorème de l'équipartition de l'énergie, the energy equipartition theorem, which is very interesting, which I also use in my models. If you have multiple modes of oscillation in an atom or molecule, or even inside of a two-dimensional structure like the electron, it can oscillate in two dimensions, vertical, horizontal, up and down, sideways, or in 3 dimensions. In 3 dimensions, then the energy must be distributed half-half or one-third, one-third, one-third. So he does discuss the black body radiation problem. His mathematical treatment is very complicated, and it's not anymore the standard one, as found, for instance, I noticed in Feynman's lectures. He gives a summary, but it has all the required elements that actually solve the puzzle, including the use of Planck's constant h, which, as I remind you, Planck rather reluctantly introduced as a Hilfsvariable. That's where the h comes from, to explain how energy states cannot be continuous, must be discrete. So it's a very lively discussion. And quite amazing. Langevin immediately points out like a perceived error in the equations of Lorentz. I'm not sure it is an error. Lorentz promises to get back to him. And Einstein's intervention is quite interesting because it foreshadows his much more straightforward handling of the problem, which he actually will present in a paper, one of the last ones. There's a letter of Lord Rayleigh, and who doesn't participate, but who worked with genes on the theory, the kinetic theory. That's a word that drops a lot. Kinetic theory. How do we explain things in terms of motion? Motion of what? Charge, electrons. They think in terms of the motion of an electron rather than a charge. So yeah, it's kind of, genes first pointed out the black body radiation problem, if you read Popular Science, but he also provided a solution to it. I didn't know that actually. But yeah, he also says we should distinguish discrete energy levels, W1, W2, etc. And then he has his own model. And it all boils down to, does it match the facts and experiments, the specific heats of gases, as we measure them and heat them and see what kind of radiation, at what frequency they send out. There's Warburg, who talks about the experimental verification of Planck's formula, which at that time is indeed very much about how black bodies, or bodies if you heat them, how they absorb and re-emit radiation. And Rubens, I don't know him. He talks about the great wavelength theory. I mean, I just scroll through these. Like Max Planck, really interesting, because it's of course the presentation of the Planck solution, the theory of quanta in its original form. Again, here also he includes a lot of statistical equilibrium conditions. I said the Planck-Einstein relationship applies to equilibrium states, and these equilibrium states, of course, in the case of the black body problem, are dynamic physical situations. He introduces the modern definition of temperature, and we see, well, and the energy is equal to h times the frequency, Planck's constant times the frequency relation, for the first time in history. Well, probably before, but the first time being shared with everyone. He talks about linear oscillations, however. And interesting also is indeed that he says, quantum of action is action, physical action. Wirkung in German is the product of a force times some distance times a time interval, and the quantum of energy, h times f, is derived from this fundamental constant of nature that he has found, and explains a lot of situation. Lorentz and Einstein comment a lot. Sommerfeld also, a very interesting discussion on atomic models. Yeah, I note here that Madame Curie, double Nobel Prize winner in physics and in chemistry, makes a lot of references to experiments. The recent discovery of Röntgen radiation, higher energy radiation. Knudsen, you have Jean Perrin, that's into les preuves de la réalité moléculaire. This struck me most probably because these people are discussing atomic oscillators, molecular oscillators, and it's only during the same conference that while amazing stuff like the quantization of nature gets discovered, together with the idea of other elementary things. Molecules. He shows, well, a molecule idea is a valid idea. He discusses Brownian motion, says can only be explained by assuming molecules. He mentions Einstein's contribution to the solution of Brownian motion. It's a very long paper, but an interesting one. Nernst comes, then it's a very Nernst again. He became rich, like Solvay, by patenting certain inventions. Had dozens of apparently the most modern cars, new cars. He was very interested in technology, and his paper is interesting because he applies the theory of quanta to a wide range of physical, chemical problems, and makes a lot of interesting references to experiments. It's just amazing to sort of see the breadth of his thinking. We have Honest, discoverer of the superconductivity. Very interesting paper. He phrases superconductivity in that thing as la disparition de la chaleur spécifique, the disappearance of the specific heat of metals and gases. And again, there is quite admiring in the description of how he practically does these experiments, how he cools liquid nitrogen and what is it, nitrogen or hydrogen. Very detailed, so everyone can do these experiments if they have sort of a minimal equipment, and that's kind of nice. You don't see that anymore in modern papers. Sommerfeld, the most nominated scientist for a Nobel Prize in physics, but he never got one. I think he got nominated over 80 times. He applies the theory of the élément d'action, Planck's quantum of action, aux phénomènes moléculaires non périodiques. The motion of molecules. He develops the, if you have Planck's quantum of action, then the principle of least action, to which Feynman also attaches a lot of importance. This integral between potential and the kinetic energy, integrated over a certain distance, sort of a nonlinear curve. He also describes Planck's theory, and it's actually the most, his description of Planck's theory is actually clearer than Planck's own description. And he said, dans tout phénomène moléculaire, l'atome prend ou perd une quantité d'action déterminée de manière universelle et de grandeur, that integral over a certain time interval, kinetic minus potential energy, integrated over time. You could also do it over distance. And he introduced for the first time also the reduced Planck quantum of action, which he explains, and it is indeed a bit, when you have a nonlinear phenomena, you're going to have h divided by 2 times pi rather than h bars. It's a very interesting discussion, very clear discussion also on the nature of kinetic and potential energy, which I often find not well explained. Einstein in the discussion remarks on how these things then actually work, and he talks about these molecules, there are electrons in them, and they receive a shock when emitting or absorbing a unit of action from light quanta, and it's very interesting how he links these theory of Sommerfeld on molecular phenomena, how Einstein brings it down to interactions between photons and electrons. Langevin, la théorie cinétique du magnétisme et les magnétons, talks about para and ferromagnetism there. Very interesting. Einstein, l'état actuel du problème des chaleurs spécifiques. His solution for the black body radiation problem, like I said, and this is pretty much the model which Feynman uses in his lectures in the 60s, and which you will find pretty much in textbooks to date, so more than 100 years ago. Interesting also his follow-up on energy conservation, entropy, and then and that's it. These are the papers, and in the conclusion générale at the end, people discuss. It's very long, the conclusions. There are some conclusions, but there's a lot of discussion on and so non-definite conclusions that then get discussed in the Solvay conferences after the First World War. But it's a very interesting remark I find from Poincaré on the, he says, when we start to think of quanta in nature, quantized discrete nature, then our use of differential equations may be impacted, and we might need a new math. I don't think that new math is there today. But I think it is an interesting remark, and I still think we're looking for mathematical models, especially to analyze disequilibrium situations that might um, might use differential equations but modified for other stuff. Briouin, another great French scientist, follows up on that remark by Poincaré, a bit in the same sense that he says we need a new math to model things. I just know that in his thank you, Ernest Solvay talks again about his own little theory, integrating gravity with, I don't know, some other theory about matter and light. I find it a bit funny because it shows that Ernest Solvay, in part, thinks he's a genius, of course, like all the other geniuses that are present there, but that he was also very much into these, despite his richness and all the practical things he had to take care of as a rich industrialist, was doing what I do, thinking about these things and developing a little theories of how things work on a worldview. I said I wanted to do a last thing about dark matter. Yeah, I said the theory of matter antimatter I think is in my worldview at least quite complete. Um, so we have this symmetry, I would say, between an electron spins in one way, a positron. When the positron, the positive charge, spins in the same direction, the magnetic moments will be opposed. So you have a symmetry there. And proton, antiproton, the same thing, and it sort of completes what Dirac basically said. If you have a theory, all the degrees of freedom in your theory should match actual physical situation. And so with matter antimatter, you have exhausted all the degrees of freedom in your theory. The spin directions, the magnetic moment. But there's a very interesting asymmetrical thing about Maxwell's equations, and that's sort of that phase. It's not a phase difference between the electric and magnetic force, but they're perpendicular to each other. The magnetic field vector and the electric field vector are perpendicular to each other. And so it's a bivector, but it's a bivector in a very specific way. The magnetic field vector is 90 degrees different from the electric field vector, but in a very specific geometry. And so I've been thinking like we could perhaps imagine an anti-force, but not anti in the sense of like antimatter. We're not talking because we have that positive and negative charges, but sort of an electromagnetic force whose when you see that bivector representation of it, where the electric and the magnetic field vector would be positioned differently. If it proceeds in one frame of reference, it would follow in another, and that's sort of there is actually in the beautiful math of Maxwell's equation, you can introduce a minus sign. You have it here. The circulation of the electric field vector is minus the derivative of the magnetic field vector with regard to time. If we put a plus sign there, you have a force that of course we can't see, and that's actually the reason why probably I think dark matter or dark energy, dark field energy would not interact with our normal matter, including antimatter, and are the fields as we know them, electromagnetic fields. But yeah, it would be a very different beast. So that's a mathematical possibility. It's an amazingly simple one. But yeah, that's a bit my idea, where if we would have sort of Maxwell's equations looking like this, writing them, this is in free space, with a positive sign instead of a negative sign, and using the geometric conventions. I said the electric field vector would be plus the rotation unit here, the imaginary unit, times the electric field vector divided by c. You would have an entirely different world, but obeying like the same mathematical equations, except for that how should I call it, a different space-time signature. That word has been used already, and it signifies something completely different. But it would be a dark world, or another signature of the of Maxwell's equations would perhaps The other interesting thing that I think should keep us busy is, in 2011, we always thought that the universe was like um, that the acceleration of the expansion of the universe was like decreasing, and now we discovered that it's actually increasing. Um, and that's kind of interesting, and that's another paper where if you really want to look at how crazy I am, then the finite universe, I speculate about that. Said about dark matter is antimatter. I left that idea, but yeah, an oscillating universe, the cosmological constant, it's a whole different ball game when you see, contrary to what we thought before 2011, that gradually the expansion of the universe is slowing down, and then the idea was then that the universe would implode back into itself, becoming a fire, or the acceleration would be steady. The universe turns into ice. Here we have something very different, and I've been thinking like one of the craziest ideas is that you have actually other universes around our universe, which are born at different times or the same time. I don't know, but that would tear our universe apart by the force of gravity, because it said gravity is a structure of the universe. So if we imagine a mega universe with, say, a lot of universes in, then yeah, they would tear our universe apart, and that's a whole different model in cosmogenesis. So already now with what I gave you, you can imagine that for astronomers, and that's what I like. It's an entirely different thing to talk about the beginning of the universe in terms of a quark gluon soup, in which charges and fields transform into each other somehow. Where what I do is basically saying, charge is conserved, and we have fields, and we had a very dense and highly energetic, charge field soup in the beginning, where there was a disequilibrium, and the Planck-Einstein relationship wasn't respected. Indeed, sort of what you see in high energy experiments, a lot of unstable things, but charge is conserved, energy is conserved, linear angular momentum is conserved. That's a whole new, but I would say also very classical theory of how the universe started. And I'm gonna have you. I'm gonna let you have fun with it. I said I do these videos because I like. I have nothing else to do than during my holiday than to say like, well, I think I put a lot of effort in these papers and a lot of thinking, and so I'm gonna promote them a little bit, and that's what I'm doing. So if you like this video, like it, and then please. I've been my papers have gone quite well. Um, I'll show you something actually. I'm getting a lot of here. Oh no, that's on the stats. Let me overall, that paper is doing quite well. You say I'm crazy, but I shot up like another 10 points. I started publishing in 2020. My interest score is apparently I'm in the top 1% bracket of open science researchers or crazies, whatever you want to call it. And yeah, I'm now in the top 20% bracket of researchers with work related to quantum physics, which I find very interesting. So I don't have any new ideas. I think my theory is quite complete. Of course, I said a lot of details have to be worked out. And that's where I invite you kindly to read the papers, be critical of them, but see what value is in there, and most of all is don't be discouraged. Have fun with it, and think for yourself. Think about what makes sense. I think there's something inside of us, a curiosity. Our mind is amazing. We do want to sort of have a worldview and know where we came from and where we're going to, and that's not in an individual sense of I'm born, I live 50, 60, 70, 80 years old, and then I die and I become senile like President Joe Biden. And somehow, I need to disappear from the scene. No, but really in a larger sense of, this amazing thing, are we alone in the universe? Is sort of the theories we're developing here, is that sort of what Hegel said, some kind of a self realization of a rationality that expresses itself, or yeah, what is it? It's the wonder of life. It's the wonder of thinking, and so that's the goal of my talks, is to make you smile. And I'll stop with this because I'm obviously in a good mood today.